Right here, we'll get a quick little video lesson here on finding a second derivative implicitly, okay, and then writing our second derivative in terms of the variables x and y. Um, Process really is essentially the same initially as when we find dy dx, the first derivative, okay. We're starting here, we want to find our second derivative, okay, so given x squared plus y squared equals 100, we want to find our second derivative. So this is the notation dy, or right there. So that Leibniz notation for second derivative. Okay, we might see this a different problem. Maybe it's in prime notation, it's saying find y double prime, something like that. Okay, but initially, okay, the process is the same. We start, okay, and we take the derivative with respect to x on both sides. Okay, so we take the derivative with respect to x on both sides. D dx of everything on the left, and then take our derivative with respect to x on the right. Now here we take the derivative of x squared with respect to x. Variables agree, same variables, so we take the derivative as normal, 2x. Then the derivative of y squared with respect to x. So here we got to really apply the chain rule. Y is a function of x. We just don't know what it is here. We can't see it. So this is really f of x in parentheses squared. So that's why we have to do a chain rule here. So we get plus 2y, and then using the Leibniz notation would be dy dx, okay? Now, if we're using prime notation, it'd be 2y prime. Okay, equals here 0. Okay, so that first step initially is the same. Now at this point, we want to solve for dy dx. Okay, so solve for dy dx. So this would imply, right? So some pretty basic algebra here. Dy dx is then equal to, if we simplify, negative x over y. Okay, negative x over y. Okay, that's our first derivative. So now to find the second derivative, well, we take the derivative again. Okay, there's dy dx. Now I take the derivative on the left, d dx of dy dx, and then d dx of, in this case, the negative. We could keep up front. Sometimes I just put it with the numerator there, put it somewhere, get negative. Over here on the left, well, the derivative of the first derivative, and notation-wise over here, that just becomes the notation for second derivative. Now over here on the right, we have a quotient rule. Okay, so we take the derivative of the numerator, d dx, the derivative of negative x with respect to x, negative 1 times y minus numerator, negative x, times the derivative of the denominator with respect to x, so that would be dy dx, and then all of that is over the denominator squared, which is then equal to negative y plus x dy dx over y squared. All right, so what we noticed when we did implicit differentiation, that our derivative was sometimes in terms of x and y, right? And most of the time what we're doing, it's going to be in terms of x and y. Now we notice here that our second derivative is in terms of, well, x, y, but also the first derivative dy dx. So now our second derivative is really in terms of those kind of three unknowns, x, y, and what dy dx is. It's pretty standard to write our derivatives in terms of just x and y. And that's easily enough accomplished by, well, we know that dy dx right here is negative x over y. So we just take that and sub in right there and replace that. Okay, so then that means that would just become negative y plus x times negative x over y all over y squared. Okay, so we just replace this negative x over y into dy dx, and now we have our second derivative here. All right, our second derivative is in terms of just x and y. Now from here, yes, it's a complex fraction. We could take care of that and simplify it and write neatly. And like multiple choice questions, you would surely have to do that. But really the process here is what the important part is for now, right? After that, it's a matter of your algebra skills to simplify this. So take a derivative, get your derivative, simplify in terms of x and y, take the derivative again, replace. Okay, so let's do a couple more here. This one, y squared equals 9x. Again, we want our second derivative. So we start, take the derivative on the left. Take the derivative on the right. Over here, we have chain rule because the variables are different, y and x. So this, we're going to have 2y times dy dx equals over here. The derivative of 9x with respect to x is just 9, which implies that dy dx is equal to 9 over 2y. Okay, dy dx is 9 over 2y. There's our first derivative. Now notice here our first derivative is just in terms of y. Now I want to take my second derivative, and before doing that, I would probably write it like this. 9 over 2y is 9 halves times y to the negative first. Okay, there's our first derivative. Now I take my second derivative. Okay, I take my second derivative. So on the left, I'm going to have the derivative of this, just notation. And then I got to apply the derivative on the right to this function. 9 halves y to the negative first. Well, that equals then what? Chain rule, negative 1 times 9 halves, negative 9 halves, y to the negative second, but then times dy dx. Okay, times dy dx. Right, but what is dy dx? Right, here's dy dx, right, in terms of x and y, in this case just y. So this was equal to negative 9 halves y to the negative second times, right here, here's dy dx, which is 9 halves y to the negative first. And then just quickly simplifying, we get negative 9 times 9, 81 over 4, negative. All right. And then we get y to the negative second times y to the negative first is y to the negative third, so over 4y cubed. And there's one that, okay, we simplified it. There's our second derivative with respect to x, okay, in terms of x and y, and in this case, just y, right? So we have that one. And one more, okay, a little more going on here, second derivative in terms of x and y. So now we got this function here, this implicitly defined function. So we want to take our derivative on the left. All this stuff, x, y squared plus 2x plus over here we got product rule, x times y squared. The derivative of x, 1 times y squared plus x times the derivative of y squared with respect to x. So that's going to be 2y dy dx. Okay. Plus the derivative of 2x with respect to x is just 2. Plus the derivative of y cubed with respect to x is going to be 3y squared dy dx. And then equals over here 0, the derivative of 3. Now we want to solve for dy dx here, which means we're going to move the y squared over. We're going to move the 2 over. We would have then this term and this term. Factor out dy dx and solve. If we do that, we're going to get dy dx equals negative y squared minus 2. And all that would be divided by 2xy plus 3y squared. So there's our first derivative. Now to find the second derivative, we take that and take our derivative on the left. The derivative on the left is going to be the notation for the second derivative. And then take the derivative on the right of all this stuff. Negative y squared minus 2 all over 2xy plus 3y squared. And you can see here we are going to have a quotient rule. So make sure you take your time, something like this. Honestly, this is going to be more complicated than any question you would have on an AP test. But what do we got? equals, let's give myself some room here, parentheses, the derivative of the numerator, right? Derivative of the numerator, negative y squared minus 2 with respect to x is going to be negative 2y dy dx. There's n prime, derivative of numerator, times the denominator, which is 2xy plus 3y squared, n prime d minus n times now the derivative of the denominator. All right, now we got to take this as my new problem. Just taking this derivative, which we have here, 2x times y. So we have a product rule. The derivative of 2x times y plus 2x times the derivative of y, dy dx, plus now the derivative of 3y squared with respect to x, 6y dy dx, and all that would be over the denominator, which is 2x y plus 3y squared. Okay, so here's our second derivative, but now it's in terms of x, y, and the first derivative. Okay, so now to get everything in terms of x and y, what do I need to do? I replace every one of these, dy dx, dy dx, dy dx, replace every one of those three with what? Right here, because that is the first derivative. Okay, so in place of dy dx, I would replace all that stuff. Okay, so we would then have negative 2y times negative y squared minus 2 over 2xy plus 3y squared times 2xy plus 3y squared minus negative y squared minus 2, 2y, 2x, negative y squared minus 2 over 2xy plus 3y squared plus 6y, negative y squared minus 2, and then all that would be over the denominator. Okay, and now we have our derivative in terms of x and y, our second derivative. So it's messy, it's big, it's kind of looks really complicated, but if you just take your time, okay, make sure I have parentheses in this case, should be fine. Think about the process. What do we got going on? We start with our original little algebraic expression here. Y implicitly defined as a function of x. Take our derivative on left and right. Okay, make sure we apply our chain rule correctly. Solve for dy dx, right? Solve for the first derivative. Then simplify. You will feel, hey, simplify this if you can. Then apply the derivative again. You'll have x, y, right? Some combination of x, y, and dy dx. And get to here. And nothing would change if we found the third derivative. We would now take the derivative of all this, okay? You'd have x, y, you'd have dy dx in it, and then we'd sub in, okay? We're not doing it. That would be very messy here. You would want to simplify this first. Okay, so that's how you take higher order derivatives implicitly, right? Make sure you watch this over. If you have any questions on it, reach out, let me know.